So we now have to come to this concept of convolution. I think I can't introduce signal processing without saying something about convolution. So here's our original signal. Here's our dense sampling. So here's what we've done in our super samples, right? We've taken a dense sampling. We didn't do an analytical Fourier transform or whatever, where we just took more samples. We reconstruct that signal, which is now this blurry edge signal because of the additional samples. And then we sample from this blurry edge signal to get to our coarse, our pixel grid level samples, right? This is what we talked about being the right thing to do. Now, we didn't have infinite samples here, so we didn't get it perfect, but we got closer than just sampling with the low frequency, right? So we're using the high frequency signals, the additional samples the additional samples allow us to reconstruct some frequencies that we can't get with the low frequency samples, and we use that signal in order to do it, right? This is exactly what we were talking about doing. Now, we didn't do it quite this way. What we did when I originally introduced this was said, take these samples and just take 4 of them and take the average and put it here. Okay, so what's going up with that? What's going on with that? So that's called convolution. So I said just take 4 samples and average them. If we talk about this more generally, we can talk about a convolution filter. So here's a signal, now written with numbers. Here's a filter, and it's going to be a weighted filter. So instead of saying average these 2 together equally, we're going to take a weighted average. So 1 times the 1, 2 times the 3, 5 times the 1, right? So the weight here is 2 and 1 on these things. We add this all up, and the convolution of this signal by this filter gives this value. And then we're going to shift over by 1. And the convolution of this signal gives this value. Now, this convolution filter is drawn offset. Typically, they're centered. So the typical thing that would happen is this convolution signal, again, this convolution filter with this signal would write the value here so that it wasn't shifting over. In this case, it's shifting over by 1 in order to make it clear what's going on, right? We're taking the weighted of this and then doing it here. And we just shift this, and then we do this across the whole thing. So this is what convolution is. If we wanted to write it mathematically, you typically see it written this way. So we have a signal. I don't know whether F or G is the signal here. And then the other one is the convolution kernel, right? So here's the filter, here's the signal. So here they are, F and G. And in general, we could have anything in those, right? So I have an arbitrary signal. I can have an arbitrarily long filter. I can have an arbitrary set of weights in this filter. So these are these 2 things. We use this star for convolution. And this summation is exactly what I was showing on the previous slide. So we can do this in 2D also. So instead of having just the numbers like this, we have I don't know how to draw it for you easily, but we can have a 2D grid, which we slide over a 2D image calculating the convolution. Here's a picture. So here's a box filter. Everything has equal weight. We have the 1/9 just so that we're not changing the average value. If we convolve an image with this, that's convolving it with a 3x3 box filter. Why is this a box filter? Because these weights are all equal. And if you think about the cross plot of this, it's going to have a square shape to it. So that's called a box filter. If these weights were in a Gaussian or something else, then it would be some other kind of filter. So here's the box filter. So we take our original image, we convolve with a box filter, right? This is just averaging, right? So here's what we did in our super sampling. We take all the weights, we call them equal, and we write out the value. So this convolution with a box filter is exactly what we're doing in our anti-aliasing that's happening on your graphics card. So here's our original image. Here is convolved with a box filter. Look, that looks blurry. That looks an awful lot like a low-pass filter, right? It looks like that's what's going on here. So indeed, it's more or less what's going on. If we take our spatial domain and we convolve with a signal to get some, in this case, blurry image that we got, right? This convolving with a box makes a more blurry image. This is the same as going to a Fourier transform. We're going to multiply by whatever is the Fourier transform of this filter. So the Fourier transform of box filter is called a sinc function. And we multiply these, and that gives us some kind of signal in the Fourier domain. And if we do the inverse Fourier, it gets you exactly back to here. So the low-pass filter is essentially cutting off the high frequencies. You see we have a bunch of high frequencies out here. They have more or less, we'll get to the details in a second, but they have more or less got rid of the high frequencies out here. So that's called a low pass filter because we're only passing the low frequencies. And that gives us a new signal. And if we take the inverse Fourier transform, we get to this. So this is called the convolution theorem. It says you can either convolve in the spatial domain or multiply in the frequency domain. It's the other way too. You can multiply in spatial or convolve in the frequency. There's a duality. So this convolution theorem says we have two options. We can pre-filter by convolution in the spatial domain. So if I, in a mathematically continuous sense, do a convolution in the spatial domain, okay, that's great. I can do that. Or transform to the frequency domain, multiply by the Fourier transform that's matching of that convolution kernel, and then transform back to the spatial domain. So now we get to the detail of why we have all of this fancy math, and we don't just say like average down. So in the spatial domain, we had a box filter. That means in the frequency domain, we have this thing that's called a sinc function. And I had it drawn on an earlier slide in 1D, here it is in 2D. And now, if I take a larger averaging window in my spatial domain, okay, it changes in the frequency domain. It's still a sinc function, it's just shrunk in size here. And so we're gonna get lower frequencies. But now what do we have to do to reduce aliasing? So now let's go back to what we said we have to do to reduce aliasing. We have to increase our sampling rate up to the Nyquist frequency. So we're going to have to pick some high frequencies and chop them off, right? If we don't want to introduce aliasing, then we have to get rid of our high frequencies and sample at an appropriate rate. So we're going to try to, we could just get more samples, right? But we can't ever get enough. If our signal is going to have infinite frequencies, we can never get infinite samples, right? We have a limited image resolution, 1024 by 1024 or something like that, right? So we have a limited number of samples. So we're going to try to chop high frequencies above some limit, or reduce if we can't remove them completely. So now, what is that going to look like? Oh, I wish I had another slide here. So you remember in our frequency domain, we said we're going to just chop down to zero everything that's outside of here. One of our problems is going to come because this sinc function has things that extend infinitely out here. And so if we just start chopping them off, we're not exactly a box filter anymore if we apply that. And so what is that going to mean in the spatial domain? There's going to be some problems. But let's try to see a graphical picture of what I'm talking about. So if we want to do a perfect convolution of everything in this window, if we were doing discrete, we're going to sum everything in the box. If we were continuous, we'll be the integral of everything in this box. So adding up everything in this box and then sticking it in this location is the same thing as take this original line, convolve it with a box filter, right? Because that's what we had after all, is a box filter. And then produce this blurry continuous signal and then sample that point in the continuous signal. Right? So if we say we're going to take this box, average it down, and get that point, we're generating the values just exactly at the samples. But if you think as a continuous mathematical function, you first could generate this blurry thing and then sample that blurry thing, right? So we're doing exactly what we're supposed to be doing by the math, right? We take all of our super samples in here. We can't do an exact convolution because we don't know the exact signal, but we take these samples. They're an approximation of the higher frequency signal, and we use that approximation to do a reconstruction that lets us sample. This slide we saw before. This is talking about the same thing. We have the higher frequency samples, we get our reconstruction, we take our lower frequency samples. So why is this thing so complicated, right? Where's the rocket science in here? Okay, let's come back to this thing. Here's our box filter that we're doing. We have this infinite extent frequency domain. So we didn't really chop off the high frequencies. We need to chop off the high frequency. So here's this sinc function. Here's drawn in 1D, right? You can see it's got pretty large wiggles. If we just chop off here, we're throwing away some real stuff. The high frequencies are not really gone. So we still are going to have aliasing left. If we choose this box filter as our way to do our averaging, we're still going to have aliasing left because we're choosing to, this is equivalent to using a sinc filter and multiplying, and that sinc filter lets these high frequencies stay out here. You could say, why don't we use, so I don't have a slide for this, but you could say, why don't we use a perfect high pass filter? Well, if we used a perfect high pass filter that really chops off the high frequencies as we go out, then unfortunately the spatial domain convolution would have infinite extent. So when I did my weighted averaging, I wouldn't be just doing a 3x3 neighborhood. I'd have to be doing a weighted average of this whole thing that goes out infinitely. And so that also can't be done. So we can't get an exact answer, right? There's the math tells us that we're not going to get to the perfect thing. There's no perfect weighting we can put on these things, which will perfectly chop off the high frequencies and then allow us to pass this Nyquist limit when we do our samples. So we will always have some aliasing. What we're talking about is how to reduce it by getting rid of as much as we can. Okay, so here's point sampling. We can see lots of aliasing that's going on in here. So here we go to box filtering, right? So we've gone from point sampling to box filtering. I still have aliasing that's going on out here. So now what am I going to do? Like, what else can I do about this? Okay, here is where I'm going to stop lecturing on signal processing. And I'm going to say that you can go learn more about signal processing. It's a major, major tool in your mental toolbox for thinking about signals and how do they work. Now, do we need it for the kind of 3D graphics you've been doing in this class? No. Do I think that a large fraction of graphics research and people doing graphics work have learned about this, at least at the level that I'm talking about here, so that they can make judgments about how many samples do I need? Yes. So is it something you should learn more about? Yes. But we can only get so far in this class. Let me give a couple of hints. We talked about a box filter. So that's just equal weights. If we start messing around with those weights, we can do better than the sinc filter in terms of cutting off high frequencies. So for instance, a common thing to do is instead use a Gaussian here, where we don't let the Gaussian go out infinitely, but the weights fall off. The Gaussian here in the spatial domain turns into something that looks like a Gaussian here. So it's not all perfect. You still have some high frequency stuff that gets left in, but it behaves substantially better and you get less. So that's one answer. But you can try to do better and better things with respect to the signal processing. Compared to audio signals and electrical signals, which tend to have not infinite high frequencies in them, graphics is annoying because we precisely have edges in graphics, and edges do produce infinite frequencies. So all of this mathematical framework of signal processing doesn't work quite as cleanly on graphics as it does on audio and electrical signals.